Okay, so now we're in Chapter 5. This is our second and last lecture in Chapter 5. We're going to jump into semi-infinite solids. We're going to spend a lot of time on this. And at first you think, semi-infinite, what does that mean? Well, if it's infinite, it's everything. But if you cut it in half, guess what? That's semi-infinite. So it's like half of the world. And you might think at first, we have transient conduction in half of the infinite space. It would be not very applicable, but au contraire, this is very, very applicable to you in your life and a lot of things that you've experienced in your life. So let's just jump into it. So they have three boundary conditions. So if you draw it like this, they'll put the x-axis running this way, starts at 0, goes off not just to L, but goes off to infinity. Semi-infinite in the space. And you have a boundary condition right here at x equal to 0, and you can have three different boundary conditions. You can just apply a specified temperature. Let's reuse the y-axis and think about temperature. And let's start this material off at a uniform temperature, T initial, which is the same temperature everywhere. And then at time equal to 0, you abruptly change it at the surface from something to another value. Boom. You just change it to the surface temperature. Pow. And then you would see that the effect of that change would propagate with time into the material. And if you're this far away, deep into the material, it probably takes a while before you sense that effect of the boundary temperature change, just being abruptly changed to a specified value. This is the most important solution, and I'll try to emphasize that. It looks like the least applicable, but it is very important. We'll spend most time on it. The other is you have a specified heat flux. So you just put, you expose that solid, which is all at some initial temperature, to a different temperature fluid with a convection coefficient. You would think that's the most applicable. But unfortunately, the MATH slows you down, the math. And yes, there's the math analytic solution. We'll solve a problem with the math analytic solution for that case. It's just very tedious and it's not as applicable as you might think. The other is, well, that was a convective. The other is specified heat flux. Think of somebody just says, I'm going to turn on a laser or something, and I'm just going to get Q double prime at that surface applied. Boom. And I'm going to push that much in, the heat flux into the solid. So these are other boundary conditions. The book covers the solution. We'll briefly touch on them, but we'll spend most of the time on specified temperature. So how could I solve for the temperature as a function of location and time? The location x goes from 0 out to infinity. And time starts at 0 and goes out to infinity as well. And in our mind, we have this changing temperature profile. So, how do you solve for that temperature profile? Well, what equation is this that we're starting with? Do you recognize that equation? What's the name of that equation? The what? The heat equation or heat diffusion equation. What's it a statement of? Conservation of energy at a point. So we derived that back in chapter 2, I think, and we've used it quite a bit. We have this. What is this equation a statement of? At all time, no, I'm sorry, at all x, but at time equal to 0, it's Ti. What is that? Initial condition, that's right. And because you have one time derivative in your differential equation, you need one initial condition. If you had a second order in time, you would need two. Maybe I need to know the initial location of my particle and initial speed. Think about dynamics, okay? But here it's so much easier than dynamics. We only have first order in time. And then we have two boundary conditions. So this is at the boundary far, far infinite. I mean, it is a semi-infinite, so where is my other side? Well, it's at x equal to infinity. And then here, x equal to 0. And here, what do we have? We just have a specified temperature. So at any time greater than 0, boom, T at x equal to 0 is changed abruptly to TS. Well, how do we solve this problem? Well, I am so glad that I don't have to reteach EA1 or EA2. Have I said that too many times? Yeah, I did. So we have a similarity variable. You've seen that similarity variable also in your fluid mechanics class, in the Blasius boundary layer profile. So we have eta as a similarity variable, x divided by the square root of 4 alpha t. Sometimes I'll put x divided by 2 square root of alpha t. Is there any difference? No, it's just whether or not you put the 2 inside the square root or not. Because if it goes inside the square root, you get square root of 4. Okay, so this is a similarity variable. What they're saying is this solution looks a lot like that solution, looks like a lot. All it is stretched out in x. So if you could just sort of, rubber band stretch it, it would lay over the next time. And then rubber band stretch it, it would lay over the same temperature profile would look like and lay over the top of the future times temperature profile. Well, now it's math. You've got it set up. You know what you want to do with a similarity variable. You want to turn this PDE into an ODE, partial differential equation into an ordinary differential equation using that similarity variable. Well, there's 3 dots right here. You have to be able to handle differential calculus and differentiation, partial derivatives, and you transform it into this ODE. This is the ordinary differential equation. Now you look at it, it's not very pretty, I agree, because it's eta times the derivative of temperature with respect to eta. We don't like that. And then we have the second derivative of temperature with respect to eta squared. You transform your initial condition and 2 boundary conditions, and then you stare at it a little bit, and what about these 2? Are they different or are they the same? They're the same. And that's one of the secrets when you use that similarity variable. Instead of having 3 additional conditions with the PDE, the 3 collapse to 2 conditions for the ODE. Here it is. These are the same. Otherwise, it wouldn't work. Okay, now I have a new problem. I have a simpler ordinary differential equation with 2 conditions. You call them boundary conditions if you like, but the similarity variable eta is, it's like a mix of space and time. And you look for the solution. There's the solution. What? Or here's your old friend. Hold it. I think you tried to write EXP for exponential of eta. No, we didn't. We wrote ERF of eta. That's not one of my friends. I don't recall that friend. It's your cousin, your long-lost second or third cousin out there in your mathematical history. It's the error function, or the Gaussian error function. So, aren't you glad you had all those hours of mathematics? And here it is. So the error function is a function of eta is equal to 2 over the square root of pi. That's just a constant. The integral starting at 0, ending at eta. That's where eta is in the function. It's the upper limit of an integral of the exp, exponential of minus u squared du. The u is that variable of integration. So you could put x there, u there, v there, something there. But here, just put it as u. So you make that integral, evaluate at the lower and upper limit, and then, boom, you have the error function. All right. What was the similarity variable again, eta? Was it the ratio of x divided by the square root of 4 alpha t? Hey, what did x stand for? The location. What did x range from? 0 to infinity. What did t stand for? Time. It went from 0 to infinity. What's alpha? thermal diffusivity. So looking at it, what are the SI units of the similarity variable eta? So why do we ask this question? Let's say somebody says, I want you to exponentiate a new variable eta. Okay, I just want you to get out your calculator and say, I want you to calculate when eta is equal to 3 seconds, calculate e to the eta. You know what? You should stop at that point and challenge the person a little bit and say, is eta equal to 3 seconds or is eta equal to just 3? Because I can't exponentiate 3 degrees C. I can't exponentiate 3 meters. I can't exponentiate 3 seconds. It doesn't make sense. What you have to feed something when you exponentiate it is dimensionless. And same thing now, we're going to have the ERF of eta. Does it make sense to have calculate the error function of 3 seconds or 3 meters or 3 degrees C or 5 whatever BTUs? No, it has to be dimensionless. And when you look at it, this is truly dimensionless. Okay. One of your great friends are your units. Master your units. This is one of the things I harp on in Thermo 1 when I teach it, right? Units will save you. You should chase your units. Okay, let's press on. So where am I going to evaluate this error function? Well, in the appendix of our textbook, they have the Gaussian error function. Here, down here, they have a reminder of the equation for it. Isn't that it? Hey, that looks a little different than what I just wrote. I wrote ERF of eta. Here they wrote ERF of W. Sometimes I'll write ERF of X. Come on now, what is it? A function of X, a function of W, a function of eta, which is, I wish they wouldn't have put W right there. But they did, and so in this table they put W. Maybe it would have made more sense if they would have put eta up there. Then they'd have put the error function of eta. But I think you can extrapolate. Okay, you know, they're taking some function of this variable. So what does W run from? 0. And then it wraps around. Then it wraps around. And where do they end calculating it? Well, they stop at 3. Oh, you could keep going to 4 and 5 and 6. But take a look at the value of the error function. Where does it start at? So the error function of 0 is 0. And then it goes up. Almost, you know, here's 0.3. That's close to 0.3. But then what happens to it? It goes 0.8, 0.9, 0.9, 0.999. Where do you think it tapers off to? 1. So are you ever going to get an error function greater than 1? Nope. So it goes between 0 and 1. All right. Now, let me show you this. Why does this textbook use the error function of eta in chapter 5, especially section 7, 5.7, and then use the error function of W instead of the error function of eta in appendix B? So what do you think? Either I don't know or IDK. I don't know. I really don't know. I just know that probably it's a stumbling spot for some students. The next thing is you'll see another one, and it looks like a typo. They'll put ERFC. What? Hey, I just got familiar again with ERF. Now it's ERFC. It's the complementary error function. It's defined as 1 minus the error function. So hopefully that's a lot to recall or digest. The error function is sometimes called the blank error function, the quadratic error function, the complementary error function, the Gaussian, the normal, or the Helmholtz. Yeah, it's just a recall. I mean, we used that name a few times. It's the Gaussian. When somebody says Gaussian, what does that mean to you? Kind of low on the high and low tails are small, and then in the middle it peaks. It's like a distribution. And if you take a look at our function, we had e to the minus something x squared or omega or w squared or eta squared. So that gives it the same type of shape. Here's some more questions. In a semi-infinite material, the temperature is often a function of time and space. Time and space. But it's related to the error function, which is a function of the similarity variable, eta. Here I'm just describing eta again, is x divided by the square root of 4 alpha t. All right? What is the value of the similarity variable when x is large? When x is large, what is the value of the similarity variable? So we stop. And I know that this term large can be a little confusing. That's why I said, hey, large is greater than, much greater than 1. That's my interpretation of large. Where if you said C, oh, that's 1. Or if you said small, much less than 1. Or 0 is 0. Okay, so hopefully large didn't trip you up. But when x is much greater than 1, what does eta do? It's large as well. It's large, right? I don't know how to describe it. It's just multiplying large by 1 over something, blah, blah, blah. And that whatever that constant is, it either makes it scale up a little bit or scale down a little bit. Now, I'm not throwing a curveball and saying, hey, let time equal to 0. No. Some finite time. All right. How about this question? What is the value of the error function, ERF, of eta? What is the value of the error function at large eta? When eta is large. And let's go ahead and show. So recall the function of error function of, let's say, eta as a function of eta. Eta can go from 0 to 1 to 5 to 10 to 100, way out there. Eta can go, right? But it basically, the error function tops out at 1. It's straight, and then it just, that's the error function. So you feed it a large value, really large value, you're going to get back close to 1. So that's the correct answer, isn't it? Yeah. All right.
I thought I never hit 1. So
yeah, I mean, it's not going to hit 1, but it's going to get really, that's the best of your answers. All right, just a simple recall. Which of the following is the similarity variable eta? We've mentioned it a couple times. It's x in the numerator. And then we had the square root. You could either put 2 outside or 4 on the inside. The way it's written here, they have 4 on the inside in a couple choices. They have 4 alpha, and then to make it dimensionless, you need that t. So what was our best option? Looks like D, isn't it? 100% correct. Man, I got to ask harder questions, so yay. So what I want to do is I want to apply the equations that we just talked about and to a problem. So if you had a slab with a thermal diffusivity given, there's the alpha, and the thermal conductivity given, and it's initially at a uniform temperature of 5 degrees C, and the surface is suddenly changed to 20 degrees C, determine the temperature at a depth of x equal to 5 millimeters at the time of 20 seconds. It's pretty much plug and chug, right? So you say, oh, I need to calculate the eta. So for this problem, the eta, the x divided by the square root of 4 alpha t, I substitute numbers and eta comes in at about 1.5. And then we come up and we say, well, the solution for the temperature was T minus the surface temperature divided by the initial temperature minus the surface temperature as a function of the error function. of eta. We put in the 1.5 in the error function. That comes back at 0.96611. And so now we can solve for the temperature at that space and time, at that location and time. Ts plus Ti minus Ts times that 0.96611. The surface temperature is known, T initial is known, and you calculate that it's 5.5 degrees C, the answer right there. So that's just plug and chug. Okay, what is the derivative of the error function? Because once I know that temperature is a function of time and location, then guess what I want to do is I want to get heat flux. Let's say get the heat flux at the surface. Well, how do I get the heat flux at the surface? I need to use Fourier's law. Fourier's law is minus k dt, or I should put a partial derivative dt dx at x equal to 0. True or false? Isn't that Fourier's law? Does it still apply? Yeah, it does. But I'm going to have to calculate the derivative of that error function. So what is the derivative of the error function? Here's the error function. Here's a review of it. That's my definition. It's kind of like I say, here's function x squared, give me df dx. Can you do that? Okay, well, here's my definition of the error function. Give me the derivative of the error function. All right, so we're going to head stop. You have to be able to do that. And basically, chain rule, however the calculus instructors explained it to you. But yes, you can take the derivative of something, which is the integral, and you have either the upper limit is the variable that you need to take the derivative with respect to, or the lower limit, or even embedded inside the integrand. It can be that way. So this is the answer. Let's grade it. Hey, look at that. People either recall the math pretty well or not. If you want to check, what did I do right here? I cropped off where I went to the internet to check this. Wolfram Alpha. How many people have ever gone to Wolfram Alpha? It's really a useful site, isn't it? It's free, it's ubiquitous, you can get to it, and then you just type in some things. And so all you have to do is say the derivative of the error function with respect to x, and kaboom! There it is. So why did we want that? Because we needed to calculate that surface heat flux. It's one thing to get the temperature distribution. The other thing is to get the rate of heat transfer in the semi-infinite material. So somebody says, this is my analytic expression for the temperature as a function of eta, but eta is a function of x and t. I am so glad that you mastered all that calculus, so I don't have to re-explain it. Because what are we going to do now? We're going to say, look, the derivative of the temperature with respect to x at x equal to 0 is the derivative of temperature with respect to eta, and then multiply that by the derivative of eta with respect to x, and evaluate all that at x equal to 0. So you say, this is the definition of eta. Can I differentiate eta with respect to x? The easy one, isn't it? This part's easy. We just did it. Then the next part is, give me the derivative of eta with respect to, or the error function of eta with respect to eta. That's the one we just worked on. All right? And so you get 2 over the square root of pi. You have to evaluate that at what? You want to evaluate it at x equal to 0. Well, when x is 0, eta is 0. All right. So now you have your pieces. You can stick in the derivative, those pieces, into the equation. Notice that you pick up this Ti minus Ts living or staying in here. You multiply by the minus K. And what did I do with the minus K? Did I drop it off? I may have, looks like I left it off or something right here. And then you pick up the flux is, you switch the order here to get rid of the minus sign, the surface temperature minus the initial temperature. And the way we do the math in the book is consistent. You start with the low initial temperature and you abruptly change it to a higher surface temperature. What is the direction of the flow of heat into the solid? Yeah, into the semi-infinite material. It's positive. We like to avoid negatives. But the math will work if you have it where it's abruptly cooled. And then you have the square root of pi alpha t. This is a little bit of a challenge. At time equal to 0, what is q double prime? Infinity. And so it's huge. But as time marches on, it calms down and then it decays because it's proportional to, q double prime is proportional to time to the minus 1/2. It's going to slow down quite a bit. All right, what is the magnitude? When is the magnitude of the surface heat flux the greatest? I just gave that answer. It's when time is 0. And it's unfortunately a mathematical infinity. Okay. So now we take the same problem and we say determine the heat flux into the slab at that time of 20 seconds. And you just do the same thing to calculate q double prime s. It's plug and chug, so I'm going to say you can do it. The equation we just showed. Somebody's wanting to get to applications, and I want to get to applications too. But the applications without the math is not worth just jumping to applications. So why don't you take your hand that hopefully has been warm. Now it's not a cold winter day. So maybe if it was a cold winter day, you would keep your hand in your pockets to keep them warm. Or even if you're outside and you're really, really cold on a cold winter day, you'll see people put them under their armpits to keep their fingers warm. Or they'll put them someplace else where their body keeps them warm, right? But we don't have to worry about that too much. But what I want you to do is make sure that your fingers are pretty warm, right? Now, I want you to take your finger and find something that's metal in this room. Briefly touch it, get the sense of how hot or cold it may feel. Don't hold it on there for a long time, but long enough to get a sense of what it feels like to touch something metal in this room. Take your finger, you got to get it back to the same condition before you touch the metal. Then go find cloth, that's easy on the seats. Then go find wood or plastic and try to touch these metal, wood, plastic, or even the carpet, something like that, cloth, carpet, and then tell me what you sense. Yes, this is a hands-on activity. Everybody needs to do it. Which one feels cold? The metal. Which one feels the warmest? Carpet, the warmest. All right, now, knowing that the air temperature in this room is about 72 degrees F. In the bottom of in the front of the room, the back of the room, the air temperature on the right side wall, left side wall, high, low, is about all 72 F. Okay. How about the temperature of this table? 72. What's the temperature of everything that you touched? What was the temperature in the room? So did the metal have a different temperature than the carpet? They had the same temperature, but you had somehow a sense of cold. Now, if you take your fingers, make sure they're back to the warm temperature, right, the body temperature, and then you touch the metal and you leave it there for a while, a long time, does it still feel cold? No, it doesn't still feel cold. So what are you sensing? Well, you would think that semi-infinite material and applications are just like non-existent. Au contraire, there are plenty of applications, and you just went through one of them. So if you take your finger, now again, you need to keep your fingers at uniform temperature, hopefully around the body temperature. What's your body temperature, internal core body temperature? 98. So you were sensing the difference between 98 and about 72. But you know, you got pretty good sensors inside your fingers. They can feel things that are hot or cold. And so actually your lips too. Your lips are very good at sensing temperature. Anybody had their mother put their lips to their forehead to check their temperature to see if they're sick or anything? Let me check your, without a thermometer. But your fingers are pretty good. All right, so what happens is you take two semi-infinite materials, A and B. You say, well, I didn't touch anything semi-infinite. For a short period of time, the metal you touched, the wood you touched, everything acts as if it's semi-infinite. It takes a while for the temperature change at the surface of the interface to be felt throughout the material. Now, if I come over here to that big metal pole on the wall, that's thicker, more metal. It'll take longer. My fingers will sense the coldness longer than just a thin piece of metal, like up here in this rail right here. Okay, so everything's relative, but for a long enough period of time or a short enough period of time, they both, your finger as well as whatever you touched, appear to be semi-infinite. Okay, so your finger may be the A. It's warmer. Maybe you have initial temperature, TA initial. Everywhere inside the finger, we tried to keep it warm. All right, then the metal or the wood or the plastic was at a lower temperature. Two semi-infinite materials brought together. You analyze or focus on a small control volume right at the interface. What is this statement right here, that Q double prime at A coming out of A is equal to Q double prime going into B? What's that a statement of? Conservation of energy. Yeah. So what goes in has to go out because it's a very thin control volume. It's just at that interface. There's no accumulation or depletion of energy. That's kind of a key concept right here. You then take your two equations we worked so hard to come up with. Do you recognize the equation? You have the thermal conductivity of the material A. You have the temperature that the surface, the interface, abruptly changes to, minus the initial or uniform temperature of A. Then you have the square root of pi alpha A T. And so both sides, see, that's all we did. We did a lot of mathematical work to get to this point. You could solve for that surface temperature, TS. It's just a weighted average of the two temperatures, A initial and B initial. So what happens is you have ability to sense temperature not too deep into your skin. I know it's a little bit into your skin. It's not at the surface of the skin that you have your ability to sense temperature. But it's pretty good. And it was sensing that the TS, instead of being, what did we say, 98 for the finger and 72, it was closer to 72 for the metal and closer to 98 for the carpet and the wood and the other material. So this is that surface temperature. Yes, sir.
Why is the KB negative?
No, it's coming out of. It's the flow is this direction and that direction.
Okay, so the flow is into, then it's positive.
It's in the. You have to do this. We solved the problem where we only analyze the X running this way. But what we're doing is we're using the solution of B is in the correct orientation, but what about A and the flux that way in A? Now you flip it around. So it's coming like that. Yep. Anybody seen this movie?
Yes.
I still need to see this movie. I've seen parts of the movie, but it's a classic movie, right? And what happens to the flagpole scene? What happens to the tongue? So, and this is worth, you can go look at it on YouTube. I'm not going to pull it up and spend some time there, but some kids in the movie are in the playground and they challenge each other to put your tongue or kiss that flagpole. And the one kid does, and then his tongue is stuck to the flagpole on a cold winter day. And what do all his friends do? Scamper off and go. And he's stuck there, right? That's the scene. Pretty funny scene, right? But is that real? And you know what? It's real, and what we just described really describes that well. Okay, somebody wrote in, you can read some of the comments on that scene on YouTube, that for years I always thought that this was fake, that one cold blah 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 morning I stuck my tongue to a gooseneck trailer to check it out, debunk the theory. Needless to say, it's real, and blah blah blah. My mom was not so happy to have to rescue me. I've taught the class. I've had people who lived in northern states come up to me and say, yeah, I had that experience too. Has anybody lived in a northern state and touched anything, either with your lips, your tongue, or even your fingers? If you're working, maybe you have gloves and you take them off and you're working and it's below, cold. You touch a metal tool, you're stuck. How long did it take for the tongue to get stuck to the pole? That fast, right? How long does it take, if you've ever touched something like that, to get stuck to your metal tool if you have cold, sweaty hands or warm, sweaty hands and you touch a cold tool in the middle of winter? I tried to rebuild an engine once and it was crazy, about 0 degrees out. Yeah, you learn very quickly. You be careful when you touch anything. Yeah. Anybody in the military up north, Alaska? Yeah. Any experiences like that? Firsthand, yeah. Okay, here's another one. You live in South Texas. You have a beverage. You like some ice cubes. You reach into the freezer and you grab some ice cubes out of the tray. Do they come off sometimes? Do you know? This is interesting. This part of heat transfer really is it's life affecting. It describes what happens to us. So hopefully you've had some of those experiences. Hopefully they've not been painful. So what you need to do is we can then estimate the thermal conductivity of a metal flagpole. Look reasonable? Specific heat density? Look reasonable? Sure. How about the human tongue? A little harder. I mean, I'd flip through the chapter and say, where's my thermal conductivity in my human tongue? But you can do a pretty good estimate, about 0.5 from the internet. And then the density and specific heat are given, or you can estimate them. And then you can do the calculation. Let's say the tongue, internal temperature, 37 degrees C. That's pretty warm. The flagpole on a cold day, winter day, -10. What's going to be that interface surface temperature if the two come together with those properties that we just evaluated? And you can make that calculation. And if it's above this, will it stick? No. If it's below, it will stick. And for this number, it comes in right around -6. So why when the interface surface temperature, your tongue and the metal pole, goes to -6, what happens? Why does it create that problem? So here's a clicker question. So the water on the tongue surface will immediately freeze to the pole, or the tongue will immediately freeze solid, or the metal pole will eventually melt. If you have a dry tongue, is it really going to freeze? No, it really is the water, layer of water molecules that go ahead and freeze, and that's why you're stuck. Now, what did the person do when their tongue was on it? What should you do if you thought about it? If your tongue was stuck to the flagpole, what would you do to try to get it unstuck? Start breathing heavy to warm it up in that area. Or get a friend to get some water and pour it on, because the water wouldn't be ice, it would be higher than 0 degrees C. Not boiling water, your tongue would then get scorched. But you know what I mean, you would try to change it. And if you waited long enough, the thickness, you would get rid of this two semi-infinite materials coming in contact. Now, you can find applications of the two semi-infinite materials, even in something, let's say in a rolling press, where you have something hot and you're hitting it and rolling over, maybe product that's coming out of a production. It could be in contact only for milliseconds. And if you're interested in what's that surface temperature or that heat flux that goes into the material, these are the equations to use. This is how you could make those calculations. And I'm sure a lot of practical manufacturing as well as other applications use these equations. How would you calculate the highest steel pole temperature at which the tongue would stick? I mean, would it stick on a -5°C day? Or would it stick on a, you can use the same equations. You can use the same exact equations, now change it around a little bit and solve for that temperature. All right, here's that solution. If it's anything below around -3.5, then it would stick. Now, we covered the most important boundary conditions. Now it even becomes more math. The math here, I would say, is challenging but still doable. The other math is like, let me just see what somebody else did for the solution and I'll trust the publisher of the textbook, right? So here is what we worked out using that error function. This gives us the temperature as a function of location and time using that error function. It's for that constant surface temperature boundary condition, and here is that very important heat flux at that surface, what's coming either into or out of that material. Now, if you have a specified heat flux, it's less applicable, and here is the solution. I'm not going to spend time trying to reestablish that solution. I tried to spend enough time up here to establish that solution. Likewise, if you have a convective boundary condition, you even get a longer solution. And notice that in these solutions you have ERFC, which is the complementary error function. And you may have a homework problem that requires you to solve and use one or two of these equations, okay? But at this point, if you're not the one deriving the equation, you're just using it, it's back to plug and chug. So here's some questions. Let's do this one. Let me cover up some. Let me cover up these two. Well, let me read them and then I'll cover them up. What are they showing in case A, B, and C? They're showing the temperature distribution in the semi-infinite material. So what's on the x-axis right here? X, X, X. And right here is the surface, x equal to 0, x equal to 0, x equal to 0. And they're showing temperature. And so up here, they're showing different temperature profiles at what? Different times. Which is the shortest time? That one. What's the longest time? That one. So shortest time, longest time, shortest time, longest time. And just by looking at the temperature profile, we should be able to determine what type of boundary conditions happening right in here. Is it a convective boundary condition? Is it a constant surface temperature boundary condition? Or a constant surface heat flux boundary condition? So let's do this. I'll pick, not make it confusing, I'll take these away, and we'll say, which of these cases, case A, B, or C, is for a constant surface temperature boundary condition? Let's go ahead and stop it and check the results. Okay. So it's not doubt, it's just A. It's a constant surface temperature boundary condition, right? Okay, let's try another one. Let's try this one. Move this up, cover that up. And which one, A, B, or C, is constant surface heat flux boundary condition? Okay, we'll stop and we'll check it out. And it is B. B. Okay, the illustration's hard to show, but for this case, the slope, and the slope right there for all three cases, wouldn't that need to be the same? Yeah, you're pushing the same heat flux into the material. Notice that for the constant temperature, very steep initially, let me clean this off, very steep initially, then the slope changes and it's less steep, hence less heat flux, and it's reducing with time. Well, the last one is this one. convective boundary condition. What's one of the keys to indicate that this is, case C is for convective boundary condition? Yeah, there's T infinity. It's kind of a giveaway. There's only one where they show the temperature profile into the material off to the left. They're sketching it in the fluid. That's really what they're showing. All right. Well, I think it builds character to do a little plug and chug every now and then. So let me just summarize this problem. We have a given thickness or a slab with a thermal diffusivity and thermal conductivity. Initial temperatures given. Suddenly it's exposed to a fluid. So there's T infinity and there's our convection coefficient. Determine the temperature at a depth and after a certain time, and there's the answer. But how do you calculate that? It's like go back here and say, conceptually it's pretty easy. At this distance and at this time, right here, what is the temperature? You know, that's what you're asked to do. And you just back up and you say, this is the equation. And what is my x? That distance into the semi-infinite material. What is my time t? What is my alpha? And then you just have your convection coefficient, thermal conductivity, and h squared, and alpha again, and complementary error function. And you just plug and chug. I didn't say these things are easy. I do say they're tedious. And so when you do it, you get some solution. And I don't know how much value that is. You get around 73 degrees C. Can you do that on homework? Do it on exam if needed. But you know, on an exam, a lot of times engineers don't like long equations. What did they do? Put it into a plot. And so I forget what figure number this is in the textbook, but you can see that this is for the semi-infinite convective boundary condition. You calculate x divided by 2 square root of alpha t. What is that? That's eta. That's all it is. And for this problem, it comes in around 0.72. So 0.5, 0.1, or 1 there. That's 0.6, 0.7, 0.72, somewhere along that line. But then you've got to calculate the next parameter, convection coefficient square root of alpha t divided by k. This really isn't engineering. This is just monkey work. This is just plug and chug. But hey, let's go through it. You calculate it for this problem, it comes in around 0.2. So it's on this red line of 0.2 intersecting this line of eta of 0.722. You kind of eyeball it, you come across, and you get that this ratio, a lot easier than using the equations with the complementary error function. And you read off about 0.04, and that gives you essentially the same temperature. Make sense? So there's two ways to handle the convection, graphically or with the equation. Well, with that, I finished this section. So this last section I want to cover is on the finite difference methods. It's down in this section. I know we're skipping this periodic heating and that, but objects with constant surface temperature or surface heat fluxes, basically we emphasize the semi-infinite solid. Skip. We need to get down to finite difference methods, and especially explicit, not implicit, in the time derivative. You took numerical methods, it's just a review of that. Let's jump into it. You get a problem like this. It says you have a slab, stainless steel, conductivity, specific heat, and density are given. It's given thickness 0 to L. L is 20 millimeters. It's initially at a uniform temperature, 75 degrees C. It is insulated on the left face. And on the right face, it's abruptly exposed to convection. We have a fluid, colder fluid at 20 C, and a convection coefficient of 450 watts per meter squared degree C. Solve for the temperature at x equal to 0. That's right here, x equal to 0. At 50 seconds time after it's been exposed to the fluid. using explicit numerical solution method, using 5 nodes, add 1 second time steps. Okay, that's a lot to swallow. First of all, you can solve this problem approximately if you just check the BO number, and you could use lump capacitance depending on the BO number, what your tolerance is for error. That'll give you a number. You could also use it for the problem that we solved not the semi-infinite, but using the analytic solution to heat diffusion. You have the BO number, you have to look up the zeta 1 and C1. Hopefully the Fourier number is greater than 0.2. I'm sure with that time it is. At 1 second, you march out to 50-second time. Fourier number is going to be greater than 0.2. You don't have to worry about one term, and you can get a good estimate, probably the best estimate analytically for this temperature at x equal to 0 at a time of 50 seconds. Now we want to solve that problem using numerical methods. So we introduce how many nodes? How many nodes? 5 nodes. So you have to put 1, 2, 3, 4, 5. Just like we did in the conduction, steady state conduction. And we have to identify what is the real estate for each of those nodes. What's the size of the control volume for each of those nodes? So we take and divide between the two, the first and the second. Divide between the two, the second and the third and the fourth, and the fourth and the fifth. So I should have numbered the nodes 1, 2, 3, 4, and 5. 5 nodes. Now right away you're going to see something that some students may make an error with. The distance for the width of the real estate associated with node 2 compared to node 1. Do you see the comparison? Node 2 has twice as much volume as node 1. And so it's easy to get off by a factor of 2 in some of these calculations. So it's like this is a full delta x. This is a delta x divided by 2. Okay. We're going to pick into the sheet of paper an area of 1 meter squared. So if somebody says, what is the volume associated with node 4? It would be delta x, a full delta x, times the area, which is 1 meter squared. And then it said, what's the volume associated with either node 1 or node 5? It would be half of that. All right. How big is delta x if L is 20 millimeters and you have 5 nodes? And can you give that to me in millimeter, please? So asking a numeric response. What is delta x for this problem in millimeters? We'll go ahead and grade that one. So you have a half of a delta x, a full, so 3 plus a half, that's 4. 4 delta x's need to cover 20 millimeters, so it's 5 millimeter, isn't it? Yeah, that's what delta x is, 5 millimeter. Okay, well, I'll persevere. So this comes in at 5 millimeter. Okay, now what I want to do is I want to solve for the changing temperature of each of those nodes in increments of time. So if you think about it, I'm going to make a little table, and we'll put space going this way. So node 1, node 2, node 3, node 4, node 5. And we'll start with time 0 and then time maybe 1 second, 2 seconds, 3 seconds, marching out in time. If you do it in 1 second time steps, you need to go out to 50 seconds. You know, that's quite a few steps to get out there, 50 steps. All right. And so we'll have a value for the temperature to begin with for each of those 5 nodes, and that's given by the initial condition, isn't it? What is my initial condition? Right there. So 75, 75, 75, 75, 75. And as we go out in time, because it's exposed to a fluid, maybe I put the fluid temperature up here as well, it's 20 degrees C. That, it's going to be lower after 50 seconds. Maybe this surface temperature would be, I don't know, 28 degrees C, and this one's 32 degrees C. Here is the answer. It's going to be 65.4 degrees C, and maybe this one wouldn't be that low cold. Maybe it's, I don't know, 51 degrees C. I'm just throwing some numbers out, showing you. We're going to populate this table by doing some numerical calculations. So, and then if somebody said, well, I want you now not stop at 50 seconds, I want you to go out to 100 seconds. Okay, no problem. Let's continue marching on in time. So how do we do this? How do we do that? Well, let me do this, kind of emphasize for each of these nodes. What I'll need to do is do an energy balance for node 1. Okay, or approximation to the differential equation. So if we do an energy balance, it would be the mass associated with node 1, the specific heat of the substance associated with node 1, the rate of change of the temperature with time for node 1 is equal to the rate at which it's flowing into the control volume. Okay, so how does it flow into the control volume, into node 1 control volume? We would just have, it's insulated at the face, the left side. We just have conduction coming in from 2. What's our model for conduction coming in? We'd have the thermal conductivity. That area, we already said that the area is going to be 1 meter squared to help with the math, divided by our distance, our length. Well, that length, is that delta x over 2 or delta x? Delta x, very good, delta x. And then we have the temperature at node 2 minus the temperature at node 1. So we discretized already for the flow using Fourier's law. We have to handle this time. So this time derivative gets replaced by the temperature at node 1 minus the temperature at node 1 divided by the time step. And at this point, some books use superscripts, superseding superscripts, before the letter, subscripts, blah, blah, blah. This book uses, and I like it, they use a P and a P plus 1. So it's a superscript, and it's P is for the time level, and P plus 1 is the future time level. Okay? And then you have the mass of node 1. Let me finish this out here. The mass of node 1 would be the density times the volume associated with node 1. Wouldn't that be? The specific heat. Okay, now this is where it's a little tricky. What is the volume associated with node 1 in terms of delta x and in terms of A? The volume associated with node 1 is delta x times A or delta x over 2 times A? Delta x over 2 times A, isn't it? Yeah, I'm just trying to help you highlight the places where I've seen a lot of errors. Or I've made errors too, of course. I make errors just like everybody else. Now this is a Ka divided by delta x. We have T2 minus T1. Now we have to say, because I'm talking about the temperature at time levels, I need to pick. Do I pick that this is P and P at the current time level, and I'm trying to get to the P plus 1 time level? If you do that, that's an explicit technique, explicit. If you put P plus 1 and P plus 1, that's implicit. Implicit. Is I want to rewrite this equation so that I can get what is my new temperature at P plus 1 time level based on everything else. And that's just algebra at that point. This was the hard part right here. Isn't that the hard part? Getting that discretized equation, because you could come in and you can cancel your A's. Can't you? Yeah. And then you can move that over and rearrange it. So let me do this. Let me move to another node. I'm going to do an interior node, and then I need to do node 5, because something special about node 5. What's over here? Convection. Yeah. Do you want to do node 3? Let's do the energy balance for node 3. So I like to say, okay, I have the conduction coming in from 4 and the conduction coming in from 2. And that's going to lead to the accumulation, the rate of change of the temperature. So I'm going to have the density and the specific heat. I have to get the volume of node 3, which is my full delta X times A, and I know that's going to cancel. And then I'm going to have the temperature at node 3 and the temperature at node 3, but the first one's at the time level P plus 1, and this is at the current time level P, and I divide by delta T. Okay? All right. Now let's do our conduction in from 4. That'll be our K, our A divided by delta X, T at 4 minus T at 3 at level P. And then we'll have Ka over delta X at node 2 coming in from to 3. And both of those are at the P level and the P level. Does that make sense? At this point, that's the hard part. I know we would rearrange the math. Maybe I should, since I have space, go ahead and rearrange the math. Let's cancel the A's because they go, okay. And then we're going to get the temperature at 3 at P plus 1 is equal to the temperature at 3 at P. I'm going to put plus K divided by rho C. Isn't that alpha? It is. Delta X squared. That's good. And then we're going to have delta T right there. Then we're going to have T at 4P. You could combine it and put 2T3 at P and then T2 at P. That's fine. But I think the way you package it, some people may package it a little different, but we did the math okay. Do you agree with that? Thumbs up? How about if I get a couple thumbs up? It looks okay? Good. Okay, I didn't lose you. Now let's move to node 5, the harder one. Because what are some people going to forget, or I might forget? The H and the T infinity. So again, for node 5, it's half of the delta X for the volume. So on our energy balance, we got the rho C, the delta X over 2 times the area, the temperature at node 5 at the new time level, minus the temperature 5 at the current time level divided by the time step, equal to, we have the convection coming in, so we'll have an HA times T infinity minus T5. I know I've emphasized this before. I like to write them all this way, as if the energy is coming into the node of interest by convection and or conduction. And some people sit there and say, but T infinity is lower than T5, so it should be flowing out. The math will work itself out. Okay. And then we have plus Ka divided by delta X, the T4 minus T5. And everything explicit method, this is at the P, and the P level. We don't really need to put a P on T infinity. You could put it on there, but it's not changing. It's constant with time. Okay, so if I have enough time, what I'd like to do, and I know a lot of you know Excel better than me, but would it be a waste or an insult if I showed you how to do this in Excel or not? Okay, let me show you how I do it in Excel. And I'm going to jump over to Excel. Well, here's my solution already. Let me do this. What do I do over here? I just put in information. I just sort of put all the givens over here so that if later the problem changed and it was 85, boom, it's done, updated, right? But here for our problem, this was 75. And then this is my T infinity. I like to put my units somewhere either with the object, like the temperature or the convection coefficient, or sometimes I'll put them over here. It's whatever style. Convection coefficient, I like to put L, rho, C. And then what happens right here, you could tell what I did in this cell. I just took and calculated alpha. It helps a little bit. Time step was given to be 1 second, and my spatial was 5 millimeter. Pick the area. So now I know the full volume for one node. You could have skipped that step. And having worked with the equations, I know that there's a grouping of terms that I'm going to use consistently. It's kind of this HA dt over MC. I know the A's could cancel. I could simplify that a little bit, but I didn't here. Or also Ka over dx times dt over MC. Those two groups just help me when I come up here and I say I'm going to march time 1, 2, 3, 4 all the way down to 50. I can scroll down. So this is pretty brute force, right? A lot of cells being consumed. And these are my nodes 1, 2, 3, 4, 5, and I even put a fluid node in. And I just put the temperature of the fluid is picked off. So if I change the temperature of the fluid to be 15, hopefully it percolates and makes the update. But leave it at 20 for this problem. And I fill in these. You can tell it's going and grabbing T1. It looks like I defined little T1 or T initial. That's I don't know if you've ever used that to define anything. Have I shown that to you? So if I wanted to use this specific heat, an equation somewhere else, I could always call it cell C7, or I could come up here and just say specific heat. And I use the underline, kind of like, hey, I'm defining this as C underline. That's my new variable. And now that is defined. So if I wanted to come to this cell and I said, look, go up here and get TI, it starts to recommend, oh, do you mean TI underscore a label that you've given to a cell? If I hit tab, it says, yeah, that's what I want. And I want to multiply it by C, and it's like right away suggesting, hey, are you looking for your, tag, this label? And I hit tab, and it says, yeah. I don't know if you ever use those. Students showed me that. I didn't learn it on my own, so that was helpful. But let's just back out of that and stop that. Okay. So this is the hard part right here. This first level, what I have to do is I have to code up for node 5. The temperature at node 5, you can see what it is. Let me double click here. Is I say go to the node 5 at the previous level and then add to it blah, blah, blah. And I'm just implementing my equation right here. Notice that I go and I grab C16, which is my grouping of parameters down here. C16. I'm using that for my conduction from 4, as well as C15, my convection from the fluid. How many people think they could implement this? I think you could, right? This looks pretty straightforward. But you see what I'm doing, so I march through in time. Notice that after the first time step, this node only uses the node 3, 4, and 5 at the previous time level. They were all 75. Its temperature doesn't change in one time step. And then this one, it takes, on the 3rd second, it's finally changed. Not at 1 second, no. Not 2 seconds, no. 3 seconds, it finally changes. Information's propagated in slowly. Okay. And then once you set that up, all you do would be like grab this formula and drag down, and Excel does the work. Hey, that's kind of nice. And so this was our answer. We were looking for the temperature at x equal to 0 at 50 seconds using 5 nodes and 1 second time increments. Was that helpful? Okay. I'd encourage you to use Excel. And this seemed to be a pretty easy problem to solve. So with that, I thank you for your attention. That's all I have today. I'll see you next week on Monday.